Controlled impedance is the characteristic impedance of a transmission line formed by PCB traces and its associated reference planes. It is relevant when high-frequency signals are propagating on the PCB transmission line. Controlled impedance is important for solving integrity issues, which is propagation of signals in PCB traces without distortion. In this demo, we will show you how to route the differential pair with 100 ohms and single-ended line with 50 ohms. Here, this is the Ethernet section with Ethernet IC and RJ45 connector. You can see the net with the receiver RX and transmitter TX section, RX clock, RX control, and RX D0, D1, D2, and D3. These are all single-ended 50 ohm traces. On another side of the IC, you can see an MDI 0, 1, 2, and 3. All these connections are 100 ohms differential pairs. To achieve the impedances, we need certain trace widths. Those will be provided by the manufacturer in the form of a stack-up.
The image given here is depicting an example of a stack-up.
In this stack-up, the layers are given. The required impedances are given, and the trace width and spacing between the traces are also given. We will be performing the following steps to achieve the desired impedances for single-ended and differential traces. In our case, for a top layer with 100 ohm traces, the width is 4.4 mils and the spacing is 7.6 mils. First, we need to add this data to our layout. Before adding this data, we need to create classes of 50 ohms and 100 ohms. Go to Design, then Classes, then Net Classes. Right-click on Net Classes, then click on Add Classes. Give this class a name, 100 ohms in our case. Go to this 100 ohms class and select the nets which are in this class and click on the arrow. In this way, all nets in the class will get assigned to 100 ohm traces. In the same way, we will create 50 ohms class. Rule setup for differential pair, 100 ohms. To set the rules for the classes we created above, we will follow these steps. Go to Design, then Rules. Go to the differential pair rules, then New Rule. Give a name to this rule, 100 ohms in this case, and double-click. We will now put the values for the top layer, bottom layer, signal 1, and signal 2. For top layers in our stack-up, the values are 4.4 mils and 7.6 mils. Add minimum width, preferred width, and max width. The minimum width will be 4.4 mils, and the minimum gap will be 7.6 mils. The impedances are dependent on the trace width and the spacing. Once we do this, we will again go to the stack-up and get the signal 1 and signal 2 values. Signal 1 and signal 2 values are 4.1 mils and 7.9 mils. Add signal 1 and signal 2 values and go to the drop-down box and select Custom Query. In the drop-down box, type Net Class and select 100 ohms. The values in the top layer and the bottom layer will be the same. The ground plane and the power planes are not to be used. Rule setup for single-ended 50 ohms. Go to Design, then Rules. Go to the single-ended rules, then New Rule. Give a name to this rule, 50 ohms in this case, and double-click. We will now put the values for the top layer, bottom layer, signal 1, and signal 2. For the top layer in our stack-up, the value is 5.6 mils. Add minimum width, preferred width, and max width, that is 5.6 mils. Go to the stack-up and add the signal 1 and signal 2 values, that is 5 mils. Go to the drop-down box and select Custom Query. In the drop-down box, type Net Class and select 50 ohms. Routing differential pair. For differential pair routing, Go to Interactive Differential Pair Routing, then Route. Now select the net and do the routing. After completing the routing step, check the values of these particular traces. Select any of the traces, go to the properties, and check the values. Here, the trace width is 4.4 mils, which is the same as a stack-up value. Now go to Report and measure primitives. Select the two traces that will give us the air gap between the two traces, 7.6 mils, which is the same as a stack-up value. Routing single-ended traces. For single-ended routing, go to Interactive Routing, then Route.
Repeat the same steps as given for differential pair routing.
Once the routing is done, check the trace width. Select the trace under Properties. You will see the trace width is 5.6 mils. That is the same as given in the stack-up. Layers contain controlled impedance. That is why we need to specify these impedances in the fab nodes. Since there can be more than one value of impedance traces per layer, separate aperture codes are defined for controlled impedance traces. Trace impedance is a critical factor in the effort to transmit signals without distortion over a trace. Impedance must match the drivers and the load.